Hi, this is Regression, and today we are going to build linear regression from scratch. Of course, I know this is a video that I already done, but there were a ton of suggestions that the audio was literally trash and they didn't really understand why the equation is there and how it's implemented in the code. So in this video, I'm going to clearly explain everything. So hope you enjoy this video. So let's get into the code. Before we get into the code, we need to understand the mathematical concept behind it. And one of the thing that everyone should be aware of is about cost function. So it's basically just the summation of the difference between predicted value and the actual value. So cost function, it's written it's JWB. So it feels weird writing with mouse. Let me correct that for you. Okay, JWB equal 1 by n summation of n I equals 1. So the I is not in the equation, but you just have to assume it's basically the sample y minus y predicted the whole square. Okay, so it's basically like you see in the drawing. We have real value and we have predicted value. It's basically the difference square. Okay, so with this equation we can get two other equation by taking let's say if you remember your 12th class, you will understand it's the partial derivative. So we can derive two partial derivative function from the cost function using chain rule. So it's nothing but it's a similar value, and I am just going to expand the y predicted a bit. So y predicted is wx plus b, okay, the whole square. And we also get another equation with respect to b, which is dj by db, I mean derivative of j with respect to b equal it's the similar equation as dj by dw, but the value changes. Okay, it's like I said, it's similar value, a similar equation, it's the same equation. So okay, so the next part is a bit more trickier than most of the people think. It's basically we need to summarize this equation into smaller. I am just by taking, we can take the partial derivative function. So you can simplify the equation by partial derivative function. So it's taken by of course 2 into something into something, derivative of something. That's how we used to say in the 12th standard for the equation, for the way to find the partial derivative. If something square, it's 2 into something into derivative of something. So that's what I'm writing here. On the next part, on the next derivative function with dj by db, we're going to write the same equation but not with the x. The reason why there is no x is because the b is 0, b is taken as 0. So basically the 2 cancels out. Okay, let me complete this equation. Okay, perfect. So So one thing that I would like to, this is the complete equation. So the next, this is also called the gradient. So now we need to write the gradient descent of function, which is w equal to like weight equal to weight minus learning rate. uh, let's just use like alpha instead of LR. Learning rate times the gradient of W, which is dj by dw, and the way we find bias is equal to bias minus learning rate into dj by db, which is the gradient of db, gradient of b. Okay, so these all are the equation that we need to make this thing work. So let's get into the code. So as you can see, I have imported some of the necessary things to to create, to make algorithm work. So the first thing, if you can look at this uh, data, this is just a basic iris data, just for the understanding purpose. So the first thing that we need to write is a class of linear regression. Okay, now we need to initialize it. Now we need two values. One is learning rate and another one is number of times that we need to train the model, the times that we need to loop until that model is trained. So I'm taking that as 1000. Okay, let's declare the instance variables, and I'm going to take let me finish, and I'm going to take self dot weight as none for now, and self dot bias as none too. Okay, the next thing that we need to do is to fit the model. For that, I am going to take two values, which is x train and y train, which is given as x and y. Then we need to find the sample and features, which is the row based number, and how many rows we have, and how many columns that we have. So in sample comma and feature equal to x dot shape, and we are going to set self dot weight as the number of zeros of, how much number column we have times the zeros. So we will be having if the number of column is n, we will be having n feature, which will be nw, n weights, and the bias is going to be 0. So the next thing that we need to do is to predict from the default value that we have, which is 0, which is basically 0 in everything. So y pred equal to np dot, as we know the equation, wx plus b. So self dot weight comma x comma self dot weight. There's a reason that I gave x there, because we need to set that, because the value w is over horizontally and the data that we train on is on vertically. So there is a chance of the dimension error. So we need to consider that the x should be as the first should be in the first place in order to be that calculation correct. Okay, now we need to loop n iter times So with that we can train or update the parameters till our model is trained. The value can be anything. I'm just giving it 1000 for convenience. You can change it by going through hyperparameter tuning. You can change the best parameter, like change it into a best parameter. So I'm looping it over. So like, let me get that inside the loop. Okay. The next thing is, let's go back to the equation. So if you go here, we don't really need the 2 and the summation part. We can just cancel that out. We can include that if in like, we can include that if we like. Even though we are using the summation, we don't technically need to write that in the equation. Yes, it is necessary when you're doing the in mathematical way, but in programmatically you don't really need that. We can cancel out the 2 and the summation, and we can do that programmatically. So the 2 doesn't really brings any value. Okay, so the next thing that we need to do is find dw, I mean the gradient of w, which will be 1 by n sample. As per the equation, it's 1 by n sample times np dot x comma y pred minus y. So basically we are finding the gradient here, and gradient of w. Then we are going to do the gradient of b. It's the same thing, but but instead of we, since we don't really have the x value, we can just sum it. If you look at this equation, we don't really have an x value to multiply with the y minus wx plus b on the dz by dpm, like the derivative of b, a derivative of j over the b. So the next thing that we need to do is to run gradient descent algorithm, so which is basically updating our weights. Self dot weight equal to self dot weight minus learning rate into self the gradient of w. Next thing is self dot bias. It's kind of similar. Minus learning rate into gradient of w, as you can see. I'm sorry, the gradient of b, as you can see. Yeah. So that's our fitting part. Let's do the prediction part. So prediction is nothing but, like, we are going to utilize the same equation that we used to predict that we used inside the loop in the initial part, where we used to predict with some weight and bias with the new x value. So it's the same equation. I'm going to copy paste it. Let's return this value here. Okay, the next thing, let's go and we can find the mean square error. It's basically taking the true y value and predicted value, and we are finding mean of their differences. Since we are using numpy, it's basically so easy. We can use np dot mean and the difference between two values that we given in. So actually it's not, we need to square it, right? It's mean square error. We need to square it. asterisk 2. Yeah. So let's see how program works. Let's call the class. Just give run the method, given values. What's the error? Yeah, okay, everything. Oh, I see the error. So the problem is basically we are having this x value. That's actually we discussed before. Actually, we are having the x value horizontally, and we are trying to I'm sorry, we are having this weight value horizontally, and we are trying to calculate it with uh, vertical values, I mean vertically aligned values. So it's gonna create dimension error. So what we can do is, instead of x, we can put transpose of x, and the calculation of, I mean, like, the calculation of derivative of uh, gradient of w. So let's run that again. Still error. hmm. Hmm. Yeah, I see the error. So it's basically I haven't really gave self to the method, so it's firing a row. Okay, now you can see we were able to predict the value, and that's how we do linear regression. Let's fire up the mean square error function. Yeah, so let's fire up the mean square error. Okay, like, as you can see, this is how we can find mean square error. So this is our linear regression, and it's so impressive that we were able to do this within 10 minutes, and that's it. So that's how we build linear regression from scratch. And I will be coming back soon with other algorithms that will help you to get a really good understanding of how machine learning algorithms work under the hood. And that's it. Signing off.